All right. So next, we are going to talk about estimating the convective transfer coefficient for a flow across the porous media. So porous media is actually very commonly encountered geometry for chemical engineering processes in absorption towers, in purifiers, in filtration systems. So usually it is defined in terms of a term called void fraction, denoted by epsilon. So porosity is epsilon. So this is the void space per unit volume. So in most applications, it ranges from 0.3 to 1, but theoretically it is upper and lower limits are from 0 to 1. Okay, so these are the theoretical limits. But for most applications, for most chemical engineering application, they are in the range of 0.3 to 0.5. So the flow around this kind of objects is basically determined by the least tortuous path. Okay, so the fluid would like to follow the least resistive path. So they don't want to go into narrow channels. They want to go through the bigger channels because there will be less friction experienced by the walls. And because it has very large surface area, all of these surface areas contributing in heat transfer. So we need to really analyze this carefully. So the way we calculate the h bar for the system is based on this this equation. So here we have epsilon. This is the void fraction. J bar. So this was one of the Colburn equation that we discussed earlier. So it is function of Reynolds number. Okay, it's a function of Reynolds number, and this equation is valid between 0.7 for a prime number 0.7, and when the Reynolds number is in this range. So again, this number, this J factor, was defined as the product of the Stanton number, and this is Nusselt number over prime number. So if you substitute everything in, here, so you have so epsilon multiplied by epsilon multiplied by Nusselt number divided by Reynolds number and Prandtl number. Okay, so we are using this equation and using the definition of here. Prandtl number is equal to 2.06 multiplied by Reynolds number to the 0.575. So if you move this equation to the right hand side, so you'll have so you also have Prandtl number to the 2/3 power here. So this will be Prandtl number to the 1/3 power, and this will be equation that you'll be obtaining. So if you want to calculate h bar, you calculate it from here. Okay, and again, if we are trying to calculate what is the heat transfer rate across, so there is an inlet here, that is an outlet here. So the fluid is coming in here, fluid is going out here. So we'll be using again the log mean temperature, because T inlet and T is the T fluid is changing as it travels across the porosity. So in this case, the T log mean will be equal to delta T in. So this is, let's say, all of the porous materials are at Ts. Ts minus T in, this is delta T in, minus delta T out, divided by delta T in over delta T out, and log of that term. So that is how we calculate the log average. And after we have the log average, so you can actually calculate heat transfer rate. Okay, so AP is the cross-sectional area. So this is total surface area of the particles. And if you want to calculate the outlet temperature, so the outlet if the outlet temperature is unknown, so you basically use an equation, exponential equation similar to the one that we had. So again, here we have two areas. So this is cross-sectional area of the bed. Here ACB, this is the cross-sectional area of the bed. V is the incoming velocity. H bar is the average. H bar, APT is the total surface area of the particle. And then we can calculate a T out from here. Again, if H out is not known, if h out is not known, you need to do iteration. You need to do an iterative approach. You need to use an iterative approach. So basically, you guess a T outlet, find T mean, this is T in plus T out over 2. From T mean, you calculate H bar, and after you have H bar, you use this equation and find T out. So T out calculated versus T out guess. So you compare these two. If they are within 10% of each other, so you have a correct answer. Okay? If not, so you do the iteration again with the T out you calculated. So that will be going back to this iteration again if the numbers are different.